Um, sorry. Hi. I'm just looking at this video. I really have abandoned any pretense to professorial dignity. I hope the informality isn't bothering you. It's 9 p.m. on I'm in my apartment. So we're going to I'm going to present the concept of a silhouette score. And again, I want to emphasize that there is no correct number of clusters. I mean, the notion of correctness is really something you have in supervised learning, where there's a right answer and you've either got it or you don't. With unsupervised learning, there's nothing like that. Some numbers of clusters might make more sense. I mean, with the penguin data set, maybe using 3 clusters made more sense than using 27 clusters would have done. But it's a decision you are making. And I'm emphasizing this because silhouette scores look objective. You get a number, you pick the biggest number. I mean, that that makes it sound like there's a single correct number of clusters, and that's simply not true. Silhouette scores can be a good jumping off place, though, if you don't have anything better to work with. So silhouette scores are initially assigned to points. Um, we're going to take some averages later on, but for now, you have a point. And that point has been assigned to a cluster. And there are other clusters as well. And we define two numbers. So this is the average distance from this point to other points in its own cluster. This is the average distance of this point to points in the nearest other cluster. Well, the silhouette score is defined from these. It's B minus A divided by the maximum of A and B. What's this about? This, when you first see this formula, this is probably nonsensical. Let's just look at some values. Let's let A be small and B be large. This is kind of the best case situation. This says that we have our clusters and our clusters are very tight and far away from each other. So a point in this cluster is close to other points in this cluster, but far away from any points in this cluster. So the silhouette score is 9.99 divided by the maximum of these is 10. So the silhouette score is 0.999. In particular, It's very close to one, which, if you mess around with this a little, you can see is the maximum silhouette score. Now suppose that A equals 1 and B equals 1. This is a bad case. This says that this point in this cluster is just as close to the points in the second cluster as it is to points in its own cluster. Not sure that these hands are helping here, but like, good Lord. Suppose we have a cluster at 0, and we have a cluster at 10, and then we have a point at 5. Well, this point has to be in one of these clusters, but it's equidistant from them. So which cluster it goes into seems completely arbitrary. That's what? Do not know why writing B equals 1 turned into such a struggle, but we're there now. So the silhouette score here is 0. Now, last case. Suppose A equals 2 and B equals 1. Well, this is bad. I mean, this is kind of bad on the face of it. It's saying that this point is closer to a different cluster than it is to its own cluster. So this is like if we have a cluster at 0 and we have a cluster at 10, and then we have an observation at 1, but we put 1 in with this cluster instead of the cluster at 0. B minus A divided by the maximum. This is negative. So in general, extrapolating a little from this, 1 is good, 0 is ambiguous, negative suggests, I want to say, misclassification. And again, that can't be quite right because this is unsupervised learning. There isn't any right classification, but it suggests that something wonky has gone on. Let me put it that way. So if every point has a silhouette score and silhouette scores close to 1, I mean, exact same thing here. This is why I put right in quotation marks. But if silhouette scores close to 1 are good and silhouette scores close to 0 or negative silhouette scores are bad, pretty intuitive what we could do here. Average all the silhouette scores. This is a measure of how good the clustering is. Then we can find these averages for different numbers of clusters. and compare. So maybe when you have two clusters, the average silhouette score is this. And when you have three clusters, the average silhouette score is this. And four clusters, that five clusters, this six clusters, that. I mean, the average silhouette scores are suggesting to you that maybe four clusters are the way to go. And we can do this very easily in Python. I'm not, again, this code is in Canvas, so you can look at it there. We see that silhouette score is a built-in thing that we can call where, well, not built into Python, obviously. We're getting it from sklearn.metrics. And I'm using the Penguin data set here, and maybe the result we'll get is a little surprising. So here are the silhouette scores. I'm graphing them. I could also have created a table, I guess, but the silhouette score is maximized with two clusters. So three species, but that does not maximize the silhouette score. And I'm glad it doesn't, because I think it really drives home what I've said, that there's no right number of clusters. Two clusters makes sense. Granted that we're only looking at two of four dimensions, but do you look at this scatter plot and immediately see three groups? Because I look at this scatter plot and I see two groups. I see a group here that I am circling with my mouse, and then I see a group up here that I am circling with my mouse. So it's not like obviously wrong that our silhouette analysis is suggesting two clusters. It's what I'd suggest if I were just looking at this scatter plot without any context. But if you're interested in penguin species, maybe three clusters is the way to go. No right answer, just sort of depending on how you're approaching this.